Hello, in this video we start our discussion of early quantum theory by talking about first ionization energies as a motivation for why we need to discuss quantum theory. To begin our discussion of ionization energies, we have a cartoon. One atom. I'm hit, I've lost an electron. Are you sure? I'm positive. And thus he was ionized. So why are we talking about ionization energies? Okay, the periodic table provides great insight into the electronic structure of atoms. As discussed in the previous video, all elements in a column are chemically similar, and in order for that to happen, it turns out that their outermost electrons have similar arrangements. So ionization energy gives an indication of this. Okay, so what is ionization energy? It's the minimum energy required to remove an electron from a gaseous atom in its ground state. So how much energy to kick an electron off? Typically, this is expressed in kilojoules per mole, the energy to ionize a mole of atoms. But your book expresses this in attojoules because from the book's perspective, you haven't learned about moles yet. So it's going to talk all about attojoules. And normally people talk about kilojoules per mole. But ultimately, if you're comparing between different elements, it doesn't matter what unit system you're in as long as it's all the same unit system. Okay, so here's the definition again. And here's some equations showing what it looks like. So if you have your atom and you remove an electron, so an electron is in the products here, it means your atom goes to a positive ion, and this is ionization energy. There is an opposite process called electron affinity for an atom to gain an electron and become a negative ion. But when we talk about ionization energies, we're always talking about making positive ions. Really, it should probably be cation energies, but we don't call it that. Okay, so first ionization energy removes the first electron. Second ionization energy, you start with the cation from the previous step, and then you take another electron off, second one. Then you can do a third step, and so on and so forth. Generally, it's less energy to remove the first electron. When you go and remove the second electron, well, the atom's already positive, so it doesn't want to lose any more electrons, so it takes more energy to take off the second electron, so on and so forth. Okay, so some properties that come out of this. Elements with low ionization energies tend to form cations readily, and they also tend to conduct electricity in solid form, i.e. metals. Because the electron can come off more readily, it can then move through the metallic bonds in a solid. Alright, on the flip side, elements with high ionization energies aren't really going to form cations, and they're not really conduct electricity. So if we plot this, the first ionization energy versus atomic number, we get this interesting pattern. So we start out and, alright, helium has the highest ionization energy. There we go. And then go across the periodic table. Alright, we start the next row from lithium all the way up to neon. And then we start the next row. Then we have sodium up to argon. Then you start again, a new row at potassium. You go through the first bit of the transition metals, and then you hit krypton, a noble gas, so on and so forth. So the elements with the lowest ionization energies are the alkali metals. The elements with the highest ionization energies are the noble gases. But this periodic pattern is interesting, and we'll get to that in a few slides. Okay, so general trends in first ionization energies. You generally increase as you go up a column, up a group in the periodic table. You also increase as you go across the period to the right. So the smallest ionization energy is down here, and the largest ionization energy is up here. This is helium up here, this is francium down here in the bottom left. The way I think about this in my head is I think that ionization energy just increases this away. It increases from the bottom left to the top right. And what that means is it increases as you go up and it increases as you go across. So in my head I just think this trend goes from the bottom left up to the upper right. Another way to see it, this fun 3D diagram shows you ionization energies. The height of each bar is the ionization energy, the first ionization energy of the elements, and then the location on the chart is the periodic table. So it shows the same kind of trend, that ionization energy increases as you go from bottom left to top right. Okay, so here's your question for this video, and look at it on the screen here with the periodic table, and then I will pop the multiple choice up into a box, and when it comes up in the box, the order of the responses may get scrambled, but the same responses will be up there. Okay, so now we're back to this idea that when you look at ionization energies across some function, either across elements as you go across the periodic table, or in this screen, across the 19 successive ionization energies of potassium, you see these periodic properties, right? So here, pretty obviously, when you look at this chart, the ionization energy required to take the first atom off, or sorry, to take the first electron off versus to take the second, third, fourth, fifth, sixth, seventh, eighth, ninth electrons off, versus then the next set and the following set, there's obviously some sort of shell structure going on here. And back to this chart, we look at it and we see, okay, hydrogen to helium, that's 2 electrons. Let me try this new pointer here that I just found out about. Here we go. Hydrogen to helium, that's 2 electrons. And then lithium to neon, that's 8 electrons. Sodium to argon, that's 8 electrons. Potassium to krypton, that's 18, 18, 32. So there's obviously some shell structure going on here. The noble gases have completely filled shells, whatever that means, which we'll get to later. And they're very stable. It takes a lot of energy to remove electrons from a noble gas. Right? This is, wrong button. This is very high, right? And then on the flip side, things with very empty shells, so say lithium has 1 more electron than helium, so it has just 1 electron in its next shell. That doesn't take very much energy to remove. So, and this has, I shouldn't say this has implications for the atom. I should say the structure of the atom, which we'll learn about coming up, has big implications for why this happens. It basically drives this effect. But we're using this to motivate the effect. Here's what we see. Why is that? So I also, while we're here, want to introduce some vocabulary words. So valence electrons are electrons in the outermost occupied shell. So say you have argon. Well, the last 8 electrons that go into this argon atom, imagine you're building it up from 0 to the number of electrons it has. The last 8 electrons are the outermost electrons, and they're in the outermost shell, and we call those the valence electrons. And then the opposite term, core electrons, are in the inner shells. We wind up using valence electrons a lot because those are the ones that interact with other elements nearby to form molecules and chemical bonds, and so we deal with the valence electrons a lot. Okay, so now the next step here is why do we have this shell structure? And so we've got a lot of work to do before we fully explain that. We need to talk about quantum mechanics first, but before we talk about quantum mechanics, we need to talk about the electromagnetic spectrum. Then after we talk about quantum mechanics, we need to talk about how electrons fit into an atom, and then the shell structure will make sense. So after we do all that, we'll come back and revisit ionization energies, and then it hopefully will make sense why this trend works. But it's definitely something we need to go about figuring out. Alright, that's the video for now. Again, make sure you watch all the way to the end to get credit for doing the question. Thanks.